As I've mentioned before, there's only a few problems we can solve in closed form. One of them is the quantum harmonic oscillator. We'll start with the quantum harmonic oscillator by looking at the classical harmonic oscillator first. Then we'll write down the Hamiltonian of the quantum harmonic oscillator, followed by a concept called commutators, which is very important in quantum mechanics. And finally, we'll talk about factoring the Hamiltonian. And in the next video, we'll actually do the solution. So, the harmonic oscillator in the classical mechanics is governed by Hooke's law. That is, the force is equal to minus kx. So it's a restoring force. And this is equal to mass times acceleration, which is mass times the second derivative of x with respect to t. The solution to this system with no friction is simply a sine and cosine. So it's x of t is equal to a times the sine of omega t plus b times the cosine of omega t, where omega is equal to the square root of k over m. Now the potential energy for a harmonic oscillator is 1/2 times kx. The harmonic oscillator is a good problem because it's a good first approximation to many interesting problems in physics. As long as the amplitude of the motion is small, many systems can be studied and modeled as a harmonic oscillator. For example, let's imagine that we have a potential that has an arbitrary shape, but it has a minimum. Around the minimum, which is at x sub 0, we can do a Taylor expansion. And the Taylor expansion about x0 looks like this. The potential as a function of x is equal to the potential at x0, right? That's the value here, plus the first derivative of the potential evaluated at x0 times x minus x0. Then 1/2, add 1/2 of the second order derivative evaluated at x0 times x minus x0 squared, right? So you can get a constant term, a linear term, and a quadratic term. Now, if we assume that we don't really care about the v0, just a constant term, it moves things up and down, and we don't have any linear terms because we're very close to this minimum, then all we're left with is a second order term, second derivative and a parabolic term, which is the harmonic oscillator. So we call k, which is the k that we have up here, equals to the second derivative of the potential evaluated at x sub 0. Well, for the quantum harmonic oscillator, we can write it in terms of a frequency, but it becomes exactly the same kind of form. So the potential in the quantum harmonic oscillator is equal to 1/2 m omega squared x squared. And if you go back and look at the classical harmonic oscillator, when you substitute in omega for k, this is exactly what you get. The Schrödinger equation then for the simple quantum harmonic oscillator is equal to E times psi is equal to minus h bar squared over 2m d squared psi dx squared plus 1/2 m omega squared x squared psi. And now if you look at this, this is the operator of the momentum squared. This operator is x squared, right? So x is a variable, but it's also an operator. So we're going to solve this in two different ways. The first way we're going to solve it is the so-called algebraic method. And in order to solve with the algebraic method, we have to define what the book calls the ladder operators. And we're going to rewrite the Schrödinger equation in terms of these ladder operators, and then use the ladder operators to simplify the solution. So if I pull out a 1 over 2m from these terms, then I get 1 over 2m times p squared plus m omega x quantity squared, all times psi, is equal to my Schrödinger equation. And the Hamiltonian clearly is simply this. So the Hamiltonian is 1 over 2m p squared plus m omega x quantity squared, where p squared is now just this term here. It's h bar squared minus h bar squared times d squared by dx squared. That's the operator, p squared. We're now going to define these two ladder operators. We call them a sub plus, a sub minus. And these are defined in a very particular way, which we'll see works out properly to give us a nice solution at the end. So a plus minus is equal to 1 over the square root of 2 h bar m omega. These are all constants, obviously. And then you have times the quantity minus plus ip. This is the p operator, momentum operator, plus m omega x, where this is the x, or the position operator. If I now write the combination a minus a plus, right? So I have a minus a plus, where the minus sign gives me the plus sign here, and the plus sign gives me the minus sign here. So I have a minus first, and this is squared, so it gives me 1 over 2 h bar m omega. Then I have ip plus m omega x times minus ip plus m omega x. I can multiply this out, and I get the following. 1 over 2 h bar m omega, p squared, plus m omega x quantity squared. That's just this term here, which the I minus I give me a plus sign, plus 1. And then I have m omega x quantity squared. And then I have the cross terms. And the first cross term is, I'm going to write it as ip times m omega x. Okay, so I can factor out a minus I omega x, and I have p minus px here. The other cross product, that is the m omega x times minus ip, I can factor out a minus I m omega, and I get xp. So I get minus im omega times the quantity xp minus px. Now these are operators. And so if you remember, the p operator, the momentum operator, has a derivative involved. And because it has a derivative involved, these two quantities are not identical. Because in this case, the operator p acts on the operator x, as well as whatever is to the right. So this is the a minus a plus, again, the same that we had before. Now, the a plus minus operators in this form almost factor the Hamiltonian, because if you look at what the Hamiltonian was, it's all the stuff in red. That is 1 over 2m p squared plus m omega x quantity squared. And so this could be the Hamiltonian. The problem is you have this term in blue left that is not the Hamiltonian, that is not 0. That last term, in classical physics, this is 0 because the p is just a quantity, it's a variable. In quantum mechanics, p is an operator, and the operator has a derivative in it. And so these two are not equivalent. Right? As we remember, x is equal to, the operator x is just equal to the variable x, but the operator p is h bar over I, or minus I h bar, d by dx. And so they do not commute. That's what we mean by commuting. That is, we can't swap them with impunity. The order matters. And we want to figure out what the order, the proper order, what this quantity gives us, right? So we're going to evaluate this quantity, xp minus px. And this is called the commutator of x and p. But let's evaluate it first, then we'll talk about commutators a little bit more. So I have x, and then I have h bar over I d by dx minus h bar over I d by dx times x. And this is not equal to 0. So we're going to define this term called a commutator. If we have two operators, a and b, the commutator of the two operators is defined as square bracket a comma b. And that can be written as in the following way. The commutator of A and B is equal to AB minus BA. So if the two operators commute, then this quantity is 0. If they do not commute, then the quantity is non-zero, and that has some profound implications. For x and p, we're going to calculate this commutator, which is this quantity here. And the way you do it is you apply the commutator, which is an operator, right? It's a combination of two operators, but it's also an operator. We're going to apply it to a test function f. So this is how you evaluate the value, the commutator relation. You apply it to a function x and see what you get out. And the test function f of x is just an arbitrary test function. So this is our commutating relation. X times h bar over I d by dx applied to f minus h bar over I d by dx applied to xf of x. Well, this is easy. This just gives me the first derivative of f times x. That's easy. I can pull out h bar over I. This second term gives me two terms. One is when I take the derivative of x, and the other is when I take the derivative of f. So the first one gives me minus x df dx, and the second term gives me, when I take the derivative of x, just gives me f. And so I have two terms that will cancel each other out. This has a plus sign, this has a negative sign, and so I'm left with h bar over I times minus f. If I bring the I above, it turns the negative sign into a positive sign, and I get that the commutator of x and p applied to f is equal to IH bar, and I get f back. So the commutator of x and p is IH bar. That's what I've written here. Finally, if I then go back up to the top equation and I replace the commutator of x and p, this by the commutator of x and p is just 1 over h bar omega times 1 over 2m times p squared plus m omega x quantity squared minus im omega times the commutator of x and p. So now we can factor the Hamiltonian with this. This is the value of the a plus, a minus a plus, and it has this commutator left over, which is non-zero. But we know what it is, it's IH bar. So we're now going to replace it with IH bar. And remember, this quantity here is just the Hamiltonian. So now we have 1 over h bar omega times the Hamiltonian. And then we have to pull the h bar omega into here. The omega cancels. And the 2m pulls in, and it cancels the m, and we get minus I over 2h bar times the commutator, which is just IH bar. So now we have cancellation of the i's, give me a minus 1, cancellation of the h's, and we get 1/2. So this now means that a minus a plus is equal to 1 over h bar omega times the Hamiltonian plus a constant, 1/2. So this operator now is related to the Hamiltonian, and we can now calculate what the Hamiltonian is in terms of these two operators. So the Hamiltonian then becomes h bar omega times the quantity a minus a plus minus 1/2. Now, if we know what these operators do to wave functions, then we know what the Hamiltonian will do to the wave function. And that's the basis for solving the harmonic oscillator with the algebraic method. Now, if we change the order of a plus and a minus, so we have a plus a minus instead of a minus a plus, we're going to get everything the same, except that we have a commutator of p and x instead of the commutator of x and p. But the commutator of p and x, just as a minus sign, is a negative of the commutator of x and p, because the commutator in this case is just a constant. It's IH bar. And so this then becomes 1 over h bar omega 8 times the Hamiltonian minus I over 2h bar times minus IH bar. Now the minus sign persists here. And so we get 1 over h bar omega h minus 1/2. And we can write then the Hamiltonian in a second form as a plus a minus plus 1/2. Both these forms are going to be useful to us. They're perfectly equivalent. It just depends on how you apply the operators, whether you apply the a plus to the right first or the a minus to the right first, and you get to choose. So now we can look at what the commutator of these two operators is, because the commutator of a minus and a plus is just a minus a plus minus a plus a minus. Right? Commutator of a minus a plus is just a minus a plus, which is this quantity here, 1 over h bar h Hamiltonian plus 1/2, minus 1 over h bar omega Hamiltonian minus 1/2. Well, clearly these two terms will cancel, and we're left with plus 1/2 minus a minus 1/2, which is 1. So the commutator of a minus and a plus is just 1. The commutator of a plus a minus is minus 1. So we can now rewrite the Schrödinger equation for the harmonic oscillator in terms of these ladder operators. And we'll see why we call them ladder operators in a short while. The energy times psi, E psi, is equal to h bar omega, a plus minus, a minus plus, plus or minus 1/2 applied to psi.